My talk will have two parts, a more general one and a case study in which I will present some results of my personal ongoing research. If one asks which of Al-Farabi's ideas had the greatest impact on today's science and society, I think only one answer is possible. One concept and one text stands out from his other innovative ideas and works by its lasting effect. It changed the way scholars were thinking about science and how they organized their disciplines. It is one of the few works of Al-Farabi which were translated into Latin 200 years after the death of its author. Indeed, it was translated twice at almost the same time. The work I have in mind is the Ihsa al-Ulum, the enumeration of the sciences. It is a rather short text. The title is an understatement. At first, it appears as a simple list of disciplines ordered by the traditional ancient categories: grammar, logic, mathematics, physical sciences, metaphysics, and politics, supplemented by jurisprudence and theology. For each discipline, short descriptions of their subject matters are given. Even if it is one of the world's first catalogues of the sciences in form of an independent work, its structure follows traditional lines. However, Al-Farabi introduced a new concept with unforeseeable consequences. According to him, each discipline is divided into two sub-disciplines, one which he calls theoretical and one which he called practical. This pair of terms had a long history. Aristotle used them in order to group scientific disciplines into such which are simply observing things as they occur, and into such which investigate human practice with all moral implications. In this sense, they were used to group the scientific disciplines. The theoretical sciences were logic, mathematics, physics, and metaphysics. The practical sciences were ethics, politics, and economics. Originally, poetics was regarded as a group apart, but later it was counted as a part of logic. In the 9th century, many Greek works were translated into Arabic, and the pair theoretikos and praktikos was literally translated and used in the same sense. Ibn Farirun, a contemporary of Al-Farabi who lived in the Sirdaria region, used the terms still that way. In his Compendium of Sciences, he represented the hierarchy of sciences in three diagrams. Instead of theoretical, he used a word meaning knowledge, as opposed to practice. In the first group, he mentions metaphysics, mathematics, and natural sciences. In the second group, politics, economics, and ethics, exactly as in the compendia of late antiquity. In contrast, Al-Farabi used the terms theoretical and practical in a different sense. He did not use them for grouping disciplines together, but he used them for splitting disciplines into two parts, a theoretical part and a practical part. The work in which he developed this idea is the Ihsa al-Ulum, the enumeration of the sciences, which was mentioned at the beginning of my talk. In its third chapter on the mathematical sciences, he starts with the science of the number. It has two parts, he says. One is the practical science of the number, which deals with the number as an object of public transaction on the markets and in civil life. In contrast, theoretical science of the number deals with numbers which are taken as absolute, insofar as they are abstracted in the intellect from concrete bodies. They are pure from anything numerable among the sensually perceptible things. This touches another concept he brought up and which had impact both in the Islamic world and in medieval Europe. According to him, human scientific activity did not begin with pure sciences, but with applied sciences. Applied sciences have material objects as their matter of investigation. How then arose the pure sciences? His answer was by abstraction from all aspects of materiality. The objects of a pure science are pure forms and their relationship to each other. Astronomy as a pure science deals with pure forms in space and time. Its method is to develop proofs based on definitions, axioms, and postulates. In fact, The greater part of Ptolemy's Almagest follows this pattern. Astronomical observations and measurements correspond to the postulates in geometry. Al-Farabi makes no secret of his fondness of pure science and sees in it the perfection of science. As a second mathematical discipline, he distinguishes practical geometry and theoretical geometry. In practical geometry, the objects of knowledge are the lines and surfaces on a wooden body, which a carpenter uses, or on a metal body, which a forge uses, or on a wall, which is used by a mason. In theoretical geometry, the objects are lines and surfaces in general as objects abstracted from anything material. The classical example of a work of theoretical geometry are Euclid's Elements, on which Al-Farabi wrote a commentary. It is significant that Al-Farabi declares the science of optics as a separate discipline and not as an applied part of geometry, despite the fact that geometry is the more general science. For him, the science of optics is a theoretical science based on definitions and hypotheses which are given in geometrical terms. He mentions also the practical possibilities in measuring inaccessible objects. Al-Farabi's notion of optics as an independent discipline was not taken over by others and remained his personal opinion, a fact on which I will come back later. In the case of music, Al-Farabi distinguishes the practical science of music and theoretical science of music. In practical science of music, the individual musical instruments and their respective melodies are discussed, while in the theoretical science of music, the intelligible character of the science and the causes of harmonies are unveiled, independent from any individual instrument. Al-Farabi's great book on music deals at length with both parts. In the case of science of the stars, one would expect that Al-Farabi would declare astrology as the practical science of the stars and astronomy as the theoretical science of the stars. However, he refrained from this. Instead, he says that the term science of the stars has a double meaning. The first is the science of the judgments of the stars, which means astrology. The second meaning is mathematical astronomy, which he calls a mathematical science. In contrast, he counts astrology among the capabilities and competencies like true dreams and other forms of divination. The point he seems to make is that the capability to foresee future events is not something that can be learned, but is a gift of very few people. This idea goes back to Aristotle's explanation of true dreams. What Al-Farabi thought of the common form of horoscopic astrology of his time, he had discussed in more detail in his work, Treatise on What is Correct and What is Not Correct in Astrology. There, he restricted the influence of the heavenly bodies to physical effects, and he warned against being guided by a horoscope in one's decisions. In conclusion, astronomy is a discipline which has no practical part and is theoretical throughout. I will finish the first part of my talk with a brief remark on the reception of Al-Farabi's concept of the theoretical and practical. I already mentioned that two translations of his enumeration of the sciences were made in the 12th century. Maybe even more important was the immediate reception in the Islamic world. Scholars began to structure their handbooks by a division into a theoretical and practical part. This was the case in medicine. The very influential work, Complete Art of Medicine, written around 980 by Ali ibn Abbas al-Majusi, was divided in a theoretical part and a practical part. It was translated into Latin as one of the first Arabic works on medicine in the 11th century. It served as a model for medical works written in Latin, and medicine became generally divided into Medicina Theorica and Medicina Practica. The study of medicine was organized that way until the modern period. Even more influential was the canon of medicine of Ibn Sina, in which the same distinction is made. I come now to the second part of my talk, in which I will refer to my own ongoing research on Al-Farabi. Until recently, no work of Al-Farabi on astronomy was available. It has been known for a long time that he had written a commentary on Ptolemy's Almagest, the most important Greek work on astronomy. Around 1980, it was believed that it is preserved in a manuscript in London, and the text was translated into Russian. However, soon it turned out that it is a text of Ibn Sina from his philosophical Summa al-Shifa. In 2011, I discovered a manuscript in the Parliament Library in Tehran with the commentary on the books 9 to 13 of the Almagest, of which I presumed that it is by Al-Farabi. In the meantime, I could corroborate this assumption since I found the second manuscript in the same library with a little more text, and finally I discovered another fragment in secondary transmission. This commentary underlines Al-Farabi's notion of astronomy as a purely mathematical science. Obviously, he's not much interested in Ptolemy's discussions about astronomical observations. He puts the focus on the descriptions of the models for the solar, lunar, and planetary orbits and the geometrical proofs. In contrast to other commentators of his time, he did not discuss the new results and achievements made in Arabic astronomy. Instead, he followed slavishly Ptolemy's text, fleshed it out, and inserted intermediary steps in the proofs. Therefore, his commentary is much longer than the text he is commenting on. There are only two places where Al-Farabi inserted his own thoughts in the text. The first is in Book 9, where he speaks about the mathematical sciences in general. As in his enumeration of the sciences, optics is mentioned as an independent discipline. This is a fingerprint of Al-Farabi's authorship. Further, he says that astronomy distinguishes itself before the other mathematical disciplines by the sublimity of its topic, the heavenly bodies and spheres, because of their supreme magnitude, a statement Al-Farabi made also elsewhere. The heavenly bodies he called divine bodies. The second place is in Book 13, where Ptolemy explains his model for the planetary motions in space. In order to comply with the phenomena, he was forced to assume extremely complicated mechanisms for the planetary motions, which were at odds with the generally assumed requirement of simplicity in nature. Ptolemy states that he was unable to construct such a mechanism for himself. From that, we may conclude that he did so for his other models of lesser complexity. After that, a more general digression follows on the notion of complexity. The human mind, Ptolemy says, has a limited capacity and can only cope with a certain number of parts in an imagined model. In contrast, God's mind has an unlimited capacity and can cope with infinitely many parts in a model as long as their motion is uniform. Therefore, a model which is too complex for humans can be simple for God. Here, for the first time, Al-Farabi criticizes Ptolemy. He says that he would not comment on this passage at all. Such consideration as those made by Ptolemy here do not belong to a mathematical science, but must be discussed in the disciplines of physics and metaphysics. And if so, he argues, the Aristotelian theory of motion must be taken into consideration. He must have had Aristotle's On Heavens and Book 12 of his Metaphysics in mind. In these texts, all motions of the heavenly bodies are described as uniform circular motions around one common center. Al-Farabi makes his position not clear in this point in his extant works. His commentary on Aristotle's On Heaven, which might have given an answer, is not preserved. His remarks on the structure of the cosmos on the perfect state can be interpreted in different ways. However, from the statement in the commentary on the Almagest, it becomes clear that he did not ascribe the Ptolemaic models physical reality as they were. Their existence, he says, is impossible. However, it would be wrong to assume that Al-Farabi preferred the cosmological model with concentric spheres, which Aristotle describes in Book 12 of his Metaphysics. Al-Farabi was well aware, as a passage in his work on the perfect state indicates, that the heavenly bodies changed their distance to the Earth, which would not be possible in Aristotle's homocentric model, in which they have always the same distance to the center. Then what was his solution? The answer is he had none. In his commentary towards the end of his remark on the topic, he proposes to begin anew in the study of the movements of the celestial bodies and to investigate them from scratch. This is a radical position and at the same time a prophetic vision. From a modern perspective, he was right. What Copernicus began, Kepler continued, and Newton completed was indeed a mathematical model of the cosmos, which was in perfect accordance with the physical principles of Newtonian dynamics. In Al-Farabi's time, there was no alternative to Aristotelian dynamics. Nevertheless, Al-Farabi's intuition that only something entirely new could lead to a solution was on the right track. Another aspect of his intellectual profile becomes clear in his commentary on the Almagest. Despite he denied the material reality of Ptolemy's models, he studied them with dedication. He must have a great satisfaction to write down or dictate in more than 1,000 pages, step by step, the proofs of Ptolemy's designs. The lack of reality was for him an advantage. To study astronomy as pure science, abstracted from all physical materiality, was for him the noblest form of reasoning the human mind can reach. I come to the end of my talk. We had seen that Al-Farabi's distinction of theoretical science and practical science was in its essence very close to the modern distinction of pure science and applied science. There is a traceable track of transmission from 10th century Baghdad to our modern scientific community. Today, we share Al-Farabi's high esteem of pure science, which is by no means a matter of course and was not shared by many societies in history. I hope, whenever you use in the future the words pure science or applied science, that you remember that it goes back to the brilliant mind after whom your university is named. I thank you for your attention.